The other day when we talked about empirical formulas, and we said empirical formulas are the simplest whole number ratios of atoms that were within a molecular or formula unit of a substance. There are another type of substance which also exists as well, and they're called hydrated compounds. We've mentioned it in class once or twice in the last couple of weeks, but just as a reminder, a hydrated compound is a chemical compound that naturally will be attracted to or absorb water molecules from the air. The interesting thing about hydrated compounds is that they always have the same formula, same general formula. The formula generally will follow by the convention of some number of salt, okay, whatever that salt might be, dot some number of x, h, oh, sorry about that, some number of x, so we got the salt dot x, H2O. Okay, so for example, we could have something like copper sulfate, CuSO4, and it is always going to naturally be attracted to 5 H2O molecules. So what that tells us is that for every one copper sulfate molecule, you're going to have 5 water molecules that will naturally be attracted to it. Again, keep in mind, we don't talk about things on the molecular level. Rather, the way we can look at this is for every 1 mole of copper sulfate, you'll have 5 moles of water that are naturally attracted to it. This does a couple of things for us. This allows us to do some very simple calculations for empirical formulas, the smallest ratios of water molecules that are attracted to salts themselves. And that's the experiment that you're going to work on next time. So really what it comes down to is the objective of your experiment is going to be to determine what is the empirical formula, the simplest ratio, of water molecules for your hydrated compound. You're going to essentially try to figure out what is the ratio of water to your salt that you're going to be working with. You're going to be given one of a couple of salts. So I wanted to go through today and do a couple of sample calculations for you to give you some ideas on what you need to be thinking about. So for example, let's say we have the percent composition of a substance, and in that percent composition we know that we've got 3.52 grams of barium chloride, BaCl2, and for every 3.52 grams of barium chloride we know that there are going to be 0.61 grams of water. Okay, so it should go by convention if we look at this general idea right here that we're trying to find what is the mole ratio of the salt to the water. So basically we want to find what is the mole ratio of barium chloride to water in this case right here. So it should be pretty obvious that what we need to do first is to convert our barium chloride and our water into moles. So how do we do that? Well, we know that for every 1 mole of barium chloride, BaCl2, there are going to be some number of grams that represent that. So we need to figure out how many grams that is. So we come over to our calculator, and what we know is we need to figure out what is the molar mass of barium chloride. So what we know is that there's 1 barium and 2 chlorides that make it up. So we go to our periodic table, and we can see that barium is down here with a mass of 137.33. We can see chlorine is here with a mass of 35.453. So when we go to our calculator, we can say we've got a mass of the barium of 137.33, and we want to add to that, parentheses, 2 times the 35.45. We're leaving it 35.45 because we want to keep it to 2 decimal places as normal. And we find out that the molar mass of barium chloride works out to be 208.23 grams per mole. So back into our calculation here, we can say that there are 208.23 grams of barium chloride for every 1 mole of barium chloride. And when we perform that calculation, we can see that it's going to be 3.52 grams of barium chloride. That's going to cancel with the grams of barium chloride down here. Okay, so that will cancel out. We're going to be left with 3.52 times 1 mole divided by 208.32. And if we go back into our calculator, 3.52 divided by 208.23 is going to equal, we want to keep our significant figures consistent. It's going to equal, we want to go with 3 significant figures right here, 3 significant figures. So it's going to be 0.0169 moles BaCl2. Okay, now we need to convert our water to moles of water. So we're going to put that over 1, multiply by every 1 mole of water is some number of grams. Okay, so we go over to back to our periodic table. Hydrogen is a mass of 1.0079 or 1.01. Oxygen is 15.999 or almost exactly 16.00. So 1 oxygen and 2 waters gives us a mass of 18.02 grams. We don't really need to go to our calculator to figure that out. 18.02 grams of H2O. If for some reason you missed that, you can go ahead and back this up and hear me explain it again. But as we perform this calculation now, we can see that it's going to be 0.61 divided by 18.02, except we have to say divided by, not dot, so divided by 18.02, and that gives us 0.0339 moles of H2O. Okay, now the steps are exactly the same. We want to try to find the ratio of barium chloride to water, so we're going to divide everything by the smallest number of moles. In this case, that's your barium chloride. So we divide this by 0.0169. This equals 1 mole of BaCl2. Divide this by 0.0169. Okay, into our calculator again. 0.0339 divided by 0.0169, and that equals 2.005, which is almost exactly 2. Okay, so we can say that's equal to, better yet, it's not equal to, it's better to say that this is going to be approximately 2 moles of H2O. So what that tells us is that the overall formula of the substance is going to be BaCl2, 1 mole of BaCl2 for every 2 H2O. So the hydrated compound, therefore, is BaCl2 dot 2 H2O. Okay, let's take a look at another example. This one is going to be nickel bromide and water. Okay, so we'll say that we start with 3.207 grams of nickel bromide, NiBr2, and we have 0.793 grams of water for a total of 4 grams. I took this from a textbook example, and if you're paying attention to the beginning of the video, you might have seen 4 at the beginning. What it read was that a 4-gram sample of nickel bromide hydrate drives off 0.793 grams of water, and it wants to know what's the empirical formula from there. So that's where those numbers came from. Let's go ahead and perform this calculation. Again, we're going to take and convert nickel bromide into moles. Every 1 mole of nickel bromide, NiBr2, is going to equal some number of grams. So we go to the periodic table first. Okay, we can see nickel is 58.69, bromine is 79.904. So we're made up of 1 nickel, 58.69 grams per mole for nickel, plus, open parentheses, 2 times our bromine right here, 79.904 grams per mole, gives us a total molar mass of 218.49 grams per mole. So we come back in here, we can see that it's going to be 218.49 grams of NiBr2. Okay, similar to what we had before, we can see that the grams of nickel bromide are going to cancel. We're going to go ahead and perform this calculation. So we're going to take 3.207 divided by 218.49, and that tells us that it's approximately 0.01468. Again, keeping 4 significant figures because we started with 4 up here. Okay, 0.01468. 0.01468 moles of NiBr2. Now we do the same thing for our water. Okay, so we go for our water divided by 1 times. What's nice about water is, or any substance for that matter, is molar mass never changes. You're going to naturally remember that every 1 mole of H2O is going to have a mass of 18.02 grams of water. It's one of those that you'll naturally remember whether you like it or not. We can see that the grams of water cancel. we can see that our calculation is going to be 0.793 divided by 18.02. 0.793, oops, 0.793 divided by 18.02, and we can see that it's 0.04401. Come back into here. We've got 0.04401 moles of H2O. Now it's a matter of dividing by the smallest numbers here. We can see that the smallest number is the nickel bromide, divided by 0.01468. That's going to equal 1 mole of nickel bromide, NiBr2, divide by 0.01468 here. Go into our calculator. We've got 0.04401 divided by 0.01468, and that equals 2.997, which is almost exactly 3. Come back over here. We can say that's approximately 3 moles of H2O to give us a formula of NiBr2.3H2O. So now the key here for your experiment is you need to try to figure out what's the empirical formula of a hydrated compound. I'm going to tell you what the salt is. I'm going to tell you it's a hydrated compound. You're going to be responsible for figuring out what is the empirical formula that exists. And then what you're going to do is you're going to compare that to the known value. So some things you want to consider. How are you going to obtain masses of a salt and masses of water? What are you going to need to do for your calculations? What are you going to need to do for your experimental setup? I think if you can really think about the resources we have available in the lab and how you can go about this, it'll be very clear and easy for you. And I'm hoping that you'll be able to work your way through this experiment with very few problems at all. So just as a reminder, you want to come in Friday ready to go, have this video watched. Please make sure you write a summary for it so we can talk about it when we get to class, and you'll be all set. So have a good afternoon, have a good next couple of days, and if you have any questions, make sure you try to see me before we start class so we can try to get those questions clarified. Thanks, guys.